Привет. Меня зовут Ziling. Well, that's all the Russian I know, so that's not going to continue much. So today I'll be talking about understanding page load. Specifically, I'm talking about page load latency. That's the time leading from clicking or some action to your page loading and a usable website available to your user. And I'll be talking both about traditional and dynamic page loads. I'll define those later. There's some few tips to avoid or things to do and how the browser works. I'll be talking about some tools I use, and most of this stuff was picked up working on YouTube. So who am I? I'm a software engineer on YouTube. I've been working on the desktop and the mobile website. I've been at Google for about 4.5 years, and prior to Google, I was at Cisco Systems, graduated from University of Washington, and I specialize in web performance. So why do we care about the web? And why do we care about page load speed? Large websites typically have customers from all over the world, and they have slow connections, they have slow CPUs, they might have a few viruses, some malware, even antivirus, that slows things down as well. And then mobile users have a lot of resource constraints in terms of memory and CPU. And especially on mobile, people are now demanding native-like experiences. So people want something smooth and really just no jank. Jank meaning drops in frame rate or anything like that during animations. So in general, slow websites turn users away. We have good data about that at Google. We've slowed down our websites and then measured the effect. And there's memory effects. So we'll slow down a website and people stop using Google or stop using YouTube. And it takes a long time for them to recover. Depending on where you are, you might just come to Google, see that it's way too slow, and you just don't come back. So it's important to keep it fast. So the two types of page load I mentioned, the first one is the traditional page load. This is also sometimes known as a cold page load, especially inside YouTube. This is the first page that the page load that the user sees. It could be a refresh. So that doesn't mean it's completely uncached. And we measure this starting when the request is sent for the page. And you can use something like the resource timing API or the navigation timing API. And it ends when the important parts of the requested page is viewable and ready to the user. The dynamic page load is the new web experience where you're trying to be very smooth and native-like. And that involves usually AJAX-driven navigation. You'll load only the parts that you need, and you only change the parts of it you need. This starts with an action that you can measure. You can measure it earlier than the cold page load because now you can have the user click involved, not just the network request. Again, it ends at the same time, ends when the important parts of the page are ready and viewable, usable by the user. A note about monitoring and performance, do this first before over-optimizing your website because you need to know if your change actually affects the user, and depending on what the makeup of your user base is, some changes might not make sense. So this was covered earlier by Mikhail's slides. This is the general response time. These rules go back years before the web. Below 0.1 seconds, the user usually experiences something as instantaneous, 1 second and seamless. And as you approach 10 seconds, you start losing their attention. And at 10 seconds, they usually lose their attention. They don't know what they're doing. They leave your site. So key thing, network dominates your load time, especially on cold loads. And so to talk about that, we'll examine a web page load. And to do that, you can use something like Chrome DevTools, which has a network panel, which will show you all the requests. And it even has cool things like screenshots right now and how's your CPU doing and everything. But for us, we actually like using web page tests. This is a tool developed by some Google developers. We have an internal instance, but it's also available at webpagetest.org. And what it does is it gives you a very easy to automate system for you to run synthetic benchmarks on your current website and with very detailed information. So I profiled HighLoad.co because that's the website that was in English that I could access. And here I put it in. I set the connection to a fairly slow cable connection in the US. I'm running one test, and I'm running it from San Jose. You can pick different locations in the world to run this test from. So I ran it, and it seems like there's some things we can improve. you can see that there's a grade up there. It's A to F, and there's a few more Fs than we'd like to see. And there's other information there, load time, first byte time, start render. We'll talk about all that. And on the bottom, there's a waterfall view showing you the network profile of your page load. So network basics, I'll try to run these fairly fast since these are well known. Use a CDN. Why? Because it gets you closer to the user. That means lower latency, lower round trip time. That's very important. You can't be faster than light. Extra DNS lookup is kind of the con of using a CDN, because if you're using a CDN, it's probably on a separate domain. And if you're using it on a separate domain, it means you have another DNS lookup, another TCP connection, possible another SSL handshake. So there's a trade-off here. That said, with the other domain, you also get cookieless requests. It's a smaller response and request size. And it's something that HighLoad could do a little better. It seems like there's a lot of pages here, or resources here, that are not being served from a CDN. That said, in the case of HighLoad, this highload.co is a pretty static website. So loading it from here, there probably isn't a lot of headers and stuff to load. Next thing, cache your static content. How do you be faster than light? Don't even do the request. So HighLoad, it's kind of doing it with e-tags, but really you want a max age or expires header, because even if you have e-tags, you have to re-request. It means you still have to redo the request. You have to ask the server, has the file that I'm loading changed? And in the case of, I'm trying to run this from San Jose, that's 289 milliseconds round trip just to tell me that I don't have to do anything, right? So that's not ideal. Next, keep your connection alive and use gzip. In web page test and the performance review, you can see kind of how your site's optimized. In this case, keep alive is typically a default setting in most web servers, so that's good. It just means don't tear down the connection every single time a resource is requested. You can reuse it, and that's usually good. Gzip, everyone knows that. You should do it, and it seems like the HighLoad CO website's not doing that right now. Next, compress your images. Pretty obvious, but not being done for the very big image here. In fact, this image is much bigger than it's needed, like many pixels larger. And what you're doing here is not only you're downloading more bytes, but the browser actually has to download the image and then say, oh, it's actually smaller than this. Let me resample and resize the image before I paint it. And that's really expensive, both on the CPU, both in network. And all you have to do is, crop it correctly, decrease your JPEG size, or use WebP, and you got a really big savings there. That's huge. Next, minifies your JavaScript and CSS. Use things like uglify, closure, compiler, UI compressor. Do that. This is great. And you can see here, jQuery is being minimized. Unfortunately, jQuery is being loaded twice. That's not great. And the second thing is probably because of Google Analytics. But do check your libraries if you're including a lot of stuff and they're trying to inject their own dependencies. You might be loading multiple versions of the same library. Minimizing first byte time. What do you do here? That means chunking. That means turning, transfer, encoding chunked. In this case, HighLoad is a pretty much static website, so it doesn't really make a huge difference. But if you have RPCs on the server, it's nice to send your static content over so the browser can have something to chew on while you do your server stuff. So next thing is to reduce the number of resources. This has gotten a little bit more complicated now because we have HTTP 2 and Speedy. But under HTTP 1, there's roughly 6 concurrent connections you have per server. And that's across all tabs, including everything. If they have like 5 tabs of YouTube open, they're using it all pretty much. So that means reduce the total number of resources you need. Icons, typically people sprite this because if you have 30 icons, you can only download 6 at a time. They're all blocking. So reduce CSS, JavaScript, concatenate all those files. But if you can serve Speedy or HTTP 2, this is commonly considered an anti-pattern. Next slide, okay. And really that's because Speedy and HTTP 2 are multiplex network protocols. Allows multiple requests over one socket, so each connection to YouTube can be shared across all tabs, and they just need one connection. It doesn't have another handshake step if you have SSL or TCP handshakes. This also reduces the need for you to sprite your images. It's a little bit more complicated than that because what you can do with spriting is that you download the entire sprite sheet, and there might be a small incremental extra stuff that you're not using on your current page, but what it does is it pre-caches the content for subsequent page loads. And if you start sharding all your things, sometimes you lose on subsequent page loads. Just make sure you know this. You can pre-cache stuff yourself. You don't need sprite sheets. Next thing it does header compression. It has faster SSL handshake. If you're using Quick, which is a UDP-based transport using Speedy, which is what YouTube uses for video serving, it has 0 SSL handshake. So if you're doing that, Quick would be really awesome. Unfortunately, it only works in Chrome right now. Hopefully, other browsers start adopting it. There's also server push. You can actually start sending things to the browser before it starts asking you. Again, in the Chrome DevTools, you can spot what protocol you're using. This page is using pretty much everything. Speedy, Quick, HTTP1, HTTP2, which is written as H2. So after the first byte, though, this is the non-networking stuff. This is when the browser starts getting really busy rendering your web page. So what does the browser have to do? Well, it has to take the CSS and HTML and it has to merge them together. The HTML parser has to create the DOM, which is the document object model, and the CSS has to be created, turned into a CSS object model. And these two are then merged together to create something called the render tree. And then this render tree is pushed out and painted. So during that render tree construction, the styles are applied, objects are laid out, which means positioned correctly on your page. And then at the same time, though, the browser still has to find what other resources it has to download. It's going to throw that into the network, and then it has to execute your JavaScript. So that's a lot of stuff. And you have to realize that the browser is mostly single-threaded. There is a rendering thread that does basically all of that, and you have one per tab. So what does it have to do? Well, that one single render thread is going to parse your HTML. It's going to style your HTML. It's going to position all your elements. It's going to then paint it, which means actually putting the pixels where it should be into some buffer, and then before it sends it off to the GPU. It has to execute your JavaScript, and it has to do any event handling. This is all types of stuff, asynchronous stuff, and also events that you don't see in JavaScript that could be synchronizing between multiple threads in the browser. There's some compositing work and all that stuff that it needs to figure out. That said, network operations are on a separate tab. Network is typically not, well, I won't say typically not blocking, but the download is done outside of your render thread. And that's because you have something called the network manager. And this network manager does all network requests across all tabs in your browser. And this allows it to do things like sharing cache, sharing connection pools, and sharing DNS and all that stuff. So let's walk through a page load. What happens? Well, you get the HTML document. The document is turned into a DOM tree. That's what the parser does. And of course, CSS is turned into a CSS object model. But like, where does that CSS come from? Well, typically, we have our CSS as a link here, right? So we don't actually see the CSS until the parser starts running through your HTML. So in essence, what's really happening OK. What's really happening is that the HTML parser is running through the HTML. It sees that CSS link. It tosses it over to the network manager. The network manager downloads your CSS. And then it throws it back, and the CSS object model is created. So there's actually some blocking action there. It's not downloading the CSS in parallel. And then the CSS object model is combined with the DOM tree. The render tree is constructed. And then we can paint it, right? No. Because you probably have JavaScript. Everyone loves JavaScript. But JavaScript is blocking. So depending on where you put your JavaScript, things can change. The browser might not be able to paint. And this is because JavaScript can read and write to the DOM. The parser, the HTML parser, is very cautious. It doesn't know if your JavaScript is going to be mutating the page. So it will pause until your JavaScript is done downloading. It's going to run that JavaScript before parsing the next HTML. That said, the browser can paint a partial page. So if you have your JavaScript in the footer or somewhere in the middle of your body, it's capable of painting the stuff above it while your JavaScript is downloading. Once it downloads and is ready, though, it's going to start running it immediately. So the general advice that people have is, yeah, put your scripts near the footer, because then you don't block. And of course, have your style sheets in the head. That's because the browser actually does not paint your page until all render blocking things are ready, and that means having the style sheets downloaded first. Otherwise, it can paint something, and the style sheets come, and it has to repaint again. That's known as a flash of unstyled content. But that said, sometimes you need JavaScript in the head. You need that stuff early. You need to do something. I'm not sure what, but sometimes it's timing. So again, because style sheets are blocking paint, if you have a script, and because the HTML parser is cautious, it's going to, even if you have an inline script, it's going to wait until the CSS is done downloading, and then it's going to run your JavaScript. But because it doesn't know if your JavaScript is going to read styles. So what does that mean? It means if you have to put JavaScript in the head, make it small, and probably put it before your style sheets. Of course, measure this because you're doing some possibly micro optimizations depending on how big your things are. But in general, keep it small, in line, above style sheets. So knowing that, render tree creation probably pauses on JavaScript, but a paint happens and it's sent off and it's displayed. What I didn't mention is something called the Preloader. This Preloader is pretty awesome. It's been around since 2008. It's also known as a speculative look-ahead pre-parser, and it has about 20% page load time when it was first launched. Things might have changed. But basically, while your parser is blocked, maybe it's running on just some JavaScript, maybe it's maybe your paint isn't happening because you have your style sheets downloading and they're huge style sheets. Well, while it's blocked, another thread goes through and rips through the rest of your HTML, and it finds other style sheets, other scripts, other images, HTML imports, and all that stuff, throws it into the network queue, and has that download while you're waiting for your script to execute or other stuff. So, whoa. Okay. So because of that, though, Chrome has a bunch of network priorities. It's not just the first come, first serve here. When it sees all those scripts the preloader has tossed in, it assigns priorities to everything. So mostly what it's doing is to make sure that your images don't wreck your page load. It's going to prioritize and make sure that your HTML is downloaded first and your CSS is downloaded second. Those are known as the highest priority and medium priority. Those are actually pretty much the highest it goes. They have a bunch of low ones. There's low, lowest, and then there's idle. They keep on adding these lower priorities. But oh yeah, the one thing is while it's downloading things that are still in the head, it puts the browser in something called layout blocking mode, which only allows one low priority request at a time. And that one low priority request is in case you have some like banner image, some hero image, some special thing that is very important to your page load. It tries to be smart about that and downloads the first thing it finds. That said, there's some consequences here because you're doing chunk transfer encoding, probably because you want your page load to be fast. You have some RPCs in the back, and you're being a good citizen by putting your script tag in the footer. Well, now the preload parser can't actually see your script until you send it over. So what's the problem with that is that, I mean, those scripts might be important, and now it's blocked, and it can't even download it. So how do you get around that? Well, there's two tags that were fairly recently introduced, actually fairly a while ago. There's the async tag, which means don't block the parser, just download it and execute it as soon as it comes in. And then there's a defer tag, which means when you see this, download it and execute it after all the HTML is ready and parsed. Defer is nice because it keeps the order of script execution. Async will just execute things as soon as they come in. But these are the tools that you can use to have your scripts downloaded faster without blocking your page. So here's an example of page load, and you can see the CSS is loaded first, but there's one image that was loaded. That's because it was in layout blocking mode, so it's loading one what is considered the hero image. And then these scripts are in the footer. Those three scripts, the jQuery, slidey, and interface.js, those are in the footer, but they're downloaded before the other images that are in the body. And that's because JavaScript has a higher priority than images. So you can take a look at what priorities you have. You go to Chrome Net Internals events, you can go and see all the crazy stuff that's happening, and priority right there. So one warning is if you use JavaScript module loaders, the preload scanner cannot see inside your JavaScript. It doesn't know what's going on. So if you have scripts that are in there, the preload scanner cannot see them. I'll have to wait until the parser gets to the JavaScript, executes it, and then it will download. The same applies to CSS loaders. So let's move on to dynamic page transitions, which I refer to as warm transitions. These are typically faster than full page loads, but we can make them even faster. There's fewer network requests because a lot of things are already downloaded. Your HTML is already there. You're downloading only special sections of it to be updated. But there's also higher expectations here, especially if you're making a mobile web app that's trying to compete with native. You need to animate between your page loads. It needs to look super smooth. You have to avoid janking the thread. Again, jank means drop in frame rate. It means anything that looks bad or like, looks like chunks are coming in or you have flashes of unstyled content. We want to hide that latency though. And our goal is really to make a website feel very seamless if you're doing a warm transition. And if you prefetch, ideally it should look instantaneous to the user. So what does that look like? And remember, jankiness can be introduced at every step. But it usually means a user input happens, something triggers a page load. It could be a click, a scroll, and it just means the user has expressed their intent to move to your next page. So what typically happens is you fire an XHR, you're going to fetch the next page stuff, and you're going to dispose your current page. And by dispose, I mean you probably have some event listeners that you should be unbinding. You have some DOM elements that you're going to remove. You probably have some animations that you're doing. And typically, you're going to run that XHR before the dispose because everything's single-threaded. You can't do them together. And so what that XHR is going to do is going to throw a request to a network manager. The network manager is going to start downloading the resource. And then it's going to come back. It's going to hit, you're going to have some onload handler. And the onload handler is going to probably mutate some DOM. You have some new HTML. You have some new things that need to be appended to the page. And then you're going to run some page JavaScript because you probably have some event handlers, some other stuff that you care about. Remember though, or I'm just introducing this, but DOM mutation, whenever you touch the DOM, it causes work. It's not free. If you put things in a DOM, the browser has to do some parsing. It has to do other work. So in this case, normally it has to parse the HTML that you just did. It has to recalculate any styles because, well, you might have had a new style sheet. You might have had, well, you have DOM nodes that match other styles. So it's going to have to figure that out. And it has to position things. It might have to reposition other elements because yours push other elements down. And then it has to paint. So that's actually a good chunk of work, especially for large page transitions where the previous page doesn't look like anything like the next page. And when you did dispose, you probably also changed some things. You did some animations. You removed some stuff. That's also going to cause some browser work. And because every single thing is on the same thread, if your stuff takes too long because your animation is running too long, that return from the XHR is going to be blocked by your paint or your browser operation. So your onload handler isn't going to actually happen until all that stuff is done. So really, there's going to be some blocking time there. So, but now we're done, right? This is really what happens, but no. Remember when I said that a page load ends when the important parts of the requested page is viewable and ready? That means you might have had loaded additional style sheets. You probably have some images. Those all matter. So more style sheets. You injected a style sheet. It goes and downloads a style sheet. Now that comes back in. Style sheet means you have to recalculate your styles. You have to relay out. You have to repaint. You have other images that come in. When those come in, there's paints as well. In addition to that, it's very common, and we did this at YouTube, is that we have other data that we're delay loading or other JavaScript that we're delay loading. If you go to the YouTube watch page, the comments are often delay loaded, and that will come in. And you have to be very careful when that happens, because if that happens at a bad time, you're going to delay other things, like the CSS. The CSS is not going to be able to recalculate your styles. So having the timing of these known and well positioned is very important. So how do we make this fast or faster? Number one is keep the render thread idle. That means delay non-essential JavaScript. It means debounce your event handlers. Some events in the browser happen way more often than they need to, and it's because of legacy reasons. Ready state change basically fires as fast as possible every single time it receives a new byte. That can be pretty terrible. Scroll resize, those also fire a lot of events. So you want to be very careful when you bind to those, because if they are handling every single event, that's going to block your render thread. And oftentimes, if you're running JavaScript animations or just animations in general, you want your JavaScript to take less than 60 milliseconds if you care about 60 FPS, which you all should. Request animation frame, that's the API that allows you to have your JavaScript run before every single paint is happening by the browser. With those tools, you should be able to make smooth animations. And here's an example. If you profile a web page, in this case, this script is running. It's 67 milliseconds. That's way too long if you care about smooth animations. And that's what it's going to look like. This is the Chrome profiler. This thing is always growing. There's always new features. It's pretty awesome. So the Chrome guys are pushing this new model. It's called Rail. And these are the timings that they want people to use, that they're going to try to optimize for, and they're going to put in tools to help you improve your website. And so their goals are, if the user can get their JavaScript below 60 milliseconds, everything should be smooth for animations. And for the beginning of interactions, you're aiming for 0 to 100 milliseconds. And that's user input response time. That means, let's say you're clicking on something to begin a drag. You have 100 milliseconds to start that. And then once that drag starts, you're animating. That means keep under 16 milliseconds. In fact, it's actually less than 16 milliseconds, because 16 milliseconds is including what the browser has to do, which is, again, recalc styles, paints, layouts, depending on what styles you're changing for every single one of these drags. So in general, you're looking at less than 10 milliseconds, and even less than that if you're on mobile. So from 100 to 300 milliseconds, this is when a noticeable delay is, from the user's perspective, they can see that something's not quite smooth. When you get above that, you're starting to slowly lose user focus, and the rest of that is pretty much the same as what I've mentioned before, over 1 second, and they lose focus, 10 seconds abandonment. So how do we make sure that we have the browser stuff fast? I mean, you can kind of control your JavaScript, but you should know about what the browser's doing and how you can make it so the browser doesn't trip up. So one thing, parse time, it's very closely associated with inner HTML. If you use that and you abuse that, it's going to take a long time. And that's because the parser, although it's fast, it still has the entire web. It has to work for everything. That means it has to work for all things that don't quite look like HTML. It's a little weird. It has to take care of all those cases. To avoid that, it's actually better to use something like create element, clone node, append child, or use template tags. This allows the browser to have a much faster way of creating DOM elements. In addition to that, inner HTML is a security issue. Anything can happen with that. And of course, do not block your parse with scripts. Here's a profile, and you can see that evaluate script is actually included in parse time because the parser is blocked. So recalc style and layout. How do we make that faster? Well, that means you mutate as few DOM elements as possible. The browser can optimize for subtrees. If you're modifying only part of the DOM, it can keep the other DOM fairly efficient when it relayouts. And this is what has popularized React, actually. React basically does this for you by doing a DOM diff, but it can be achieved in many ways. Then the next thing is to reduce the size of your DOM. The rule of thumb is, especially for mobile web, keep your elements under 3,000. There's a big asterisk with that because if you have a lot of display none, they're actually much cheaper. And depending on your DOM elements, different DOM elements have different expenses. But the rule of thumb is 3,000 because the fewer elements that you have, the faster the browser can be when it's trying to do the layout, because layout has a lot of interactions between different DOM elements. And of course, simplify your CSS. So there's some crazy selectors out there that I've seen, and they're not always performant. Hide things that are not visible. Display none means that it is removed from the render tree, and if it's not in the render tree, it doesn't get painted, and that makes things cheaper. And of course, avoid mutating style sheets, because if you start mutating your style sheet that you have, the browser has to reinterpret that, reconstruct the CSS object model, and then doesn't know what's changed, so it thinks everything's changed, and it has to remerge the trees completely. So again, from DevTools, recalculate style. That's what it's called in Chrome. In Firefox, it's called reflow. And there's a few other words for it. But there's recalculate style and layout is common of what these are named in Chrome. So speeding up paints. this can be an entire talk by itself. So I'm just going to go over some cool things. One is on mobile web, Chrome now has GPU rasterization. Other browsers, some of them, I think Safari has already had them, i.e. Might on mobile web. But you have to have these special characters in your viewport meta tag to do it. But what this does is it turns the paint from something that's done in software on the CPU to parallelizable on the GPU. And that's way better. And there's a way to see if you have GPU rasterization is to turn on the FPS meter in Chrome. If it's off in this case, it says GPU raster is off. This is not available on desktop browsers right now, but it will be coming soon, they say. And another way is to use GPU layers. And this is a whole complicated topic as well. But what a GPU layer is, it allows you to have a separate texture that is painted to by the browser and is sent down to the GPU. So if you're doing an animation, it doesn't have to repaint the entire page. It can just take your element or whatever it is that you've painted into a small chunk and then move that wherever it needs to be. That said, be careful, do your research. You don't want to create too many GPU layers because then there's a lot of bookkeeping that Chrome has to do. So networking for dynamic pages, this is a lot simpler in many ways because you have less stuff to do. But because you're not in a cold load situation anymore, you don't have layout blocking mode, which means if you value your images over Ajax, or Ajax or JavaScript JavaScript downloads, you should be careful because images are lower priority than your JavaScript. So if you're delay loading JavaScript, it could block your images. And of course, in HTTP1, if you cancel a request, it shuts that socket down. That can be really bad. If you need that later, it has to redo the handshake. It has to redo any SSL stuff. So in summary, profile your page loads. I recommend webpagetest.org. If you have the resources, setting up one yourself would be really awesome. You should make your page transitions seamless. We should really make mobile web a lot better than what it is right now. And make sure you understand how browsers load your page. That's both loading for cold loads and an intra-site load. And make sure you analyze your render thread, know what's going on, and know what you're doing to the browser when you tell it to do something. So, questions? No. No.
Напоминаю, что я могу помочь, если у вас есть сложности, задать вопросы по-английски. Но поднимайте руки, если у вас есть, в любом случае.
Thank you for your speech. When you said that meta tags make GPU layers on mobile phones, few slides, and yeah, here. Minimal scale and device width make all page one GPU, big one GPU layer. Is it true?
It's a little bit more complicated than that. It doesn't make it a one GPU layer. Your page is turned into tiles.
Oh, okay.
And then those pieces of tiles are sent down to the GPU.
And all page will not be rasterized as all big GPU layer. It's
sliced up into small pieces, but that's true even without GPU rasterization.
No, okay.
What GPU rasterization does is it puts the paint which pushes all the pixels into these little buffers. It puts that on the GPU instead of doing it inside of your CPU.
No, okay. Yeah. Thank you.
Hi. About SPDI. Have you tried? Have you made the tests to see if the combining the regular technique of combining all JavaScript into one? SPDY should do the same thing when it processes all the JavaScript in parallel. So does the SPDY makes the one big JavaScript work worse than the different JavaScript files?
Yeah, so that's a good question. So yes, so it's considered an anti-pattern, right, to merge all your resources now, because you can have better cache granularity if you split it up. But you have to be very aware of how you load this. If you load it through XHR, for instance, if you delay load your modules and then you do it later, and you XHR all of them in as separate things, there's actually an overhead with creating the XML HTTP request. This was actually a result that the Google.com found. They tried to shard all the JavaScript files and then they delay load them later using XHR, and I found out that it was really slow. But in general, for a cold page load, there shouldn't be a big difference. It should be as fast, if not faster, than concatenating all your files and downloading
Do you do in Google? Do you do any different scenarios of, for example, script tags? Do you do like one big file for HTTP1 and separate files if you notice that there is a SPDY or HTML,
Right.
HTTP2?
So at YouTube, at least, right now we're still in the experimental stage with sharding our files. So that's, again, there's a lot of complexities with your site. Like if we do that, it's the same thing with the CSS spriting. When you de-sprite, you don't pre-cache next loads. And for us, next loads are super important because on the watch page of YouTube, the related videos, a lot of our traffic comes from people clicking those. Or a lot of traffic comes from people searching or going from the home page to the watch page. And those are all warm loads. And so in our case, sometimes when you shard too much and you don't load the script files that are important for subsequent page loads, you can slow down that next page load. And that next page load is the majority of our loads. So that's...
So what do you do?
So right now, we're trying to figure that out. But pre-caching things ourselves is something that we're doing.
Okay, thanks.
But yeah.
What metric do you use as a real user measurement for page load time? What is it technically?
It's the metric we use to determine what's important to the user, right? Is that what you're asking for? Mm-hmm. Yeah, so this depends on the page. It's in Mikhail's talk, he talked about the watch page. The watch page, the most important thing that we care about is the video playing. And so we basically measure and time and store all this information up until the video starts playing. Once the video starts playing, we're saying, oh, we got what we need, and we'll send that information over to the server. For other pages, it means possibly the thumbnails for the search page have loaded, including all the data for whatever the viewport size is above your above the fold, as we call it. And that's true for both the home page and the search page. But for the watch page, it's going to be the video. And this is going to be different depending on what site you have. You really should figure out what's the most important thing on your page. What does the user care about? And maybe it might be more than one factor. It might be two things, and you should probably wait for whichever one is the slowest. Yeah.
Okay, thank you.
Еще вопросы? Хорошо, тогда thank you again for your talk. Я думаю, вы сможете поймать ребят после и задать им вопросы.